Okay, so let's start. So some of your friends, they kept asking me, Hocam, I know that it's a little bit hard of a, like hard concept, this whatever quasi-concave. You can think of it as, concave-ish, okay? It's not concave, but it's concave-ish, okay? So it's not, so basically, but what you can think of is that don't forget that. So don't forget that actually this utility function, remember, so it's basically, remember the example that I gave you. So if I have a dome in this classroom, okay? So suppose I put this on an, let's say, like suppose it's on an XY plane. So this is basically, right? So I put the cone, let's say, in here, okay? So let's put it like this, so to be proper. I know that it's a little bit hard to visualize, but suppose I have, so this is basically X, this is Y, okay, and this is my utility level, okay, if I have two goods, okay. So basically, suppose I have a dome, okay, here. So basically, this is actually a perfect dome. It doesn't look like a perfect dome, but you get it, right? So I have a cup, I flip it like this, and then put it in this classroom, okay? So I put the Hagia Sophia's dome in this classroom. And then remember, at these different utility levels, I take slices of this, basically, dome, right? So at these different utility levels, for instance, I took a slice of this. And then I take the projection, okay? So those slices would be on an XY plane. They would be like this, right? So this is, here we say that the utility function is concave, okay? If it's concave, we have this nice indifference curves, and remember we get rid of the top because of more is better. And then, we have all these nice indifference curves and such. But we said that concavity is too much. It's okay for us if it's concave-ish, okay? And these concave-ish versions is, for instance, instead of a dome, you can actually have a cone like this, okay? Or even, so this also has nice sides. Instead of this perfect cone, you can actually have a pinched cone. Like the sides are like this, okay? So basically, so this is, if you want to figure out what quasi-concave looks like, you can actually think of it as that, this is also quasi-concave because it's concave, right? But it doesn't have to be like a dome, but it could be actually like a pinched cone. The sides are like this. So this will also, both of these guys would also, this is X, this is Y, this would also give indifference curves like this, but the frequency would be different, obviously, right, compared to a dome. And actually, if you have a pinched cone, it would also give you, like level curves like this, okay? So when you slice it at the same utility level, this is also going to give you those guys. This is also going to give you these kind of guys, okay? So these guys, these three-dimensional objects are utility functions. These objects, two-dimensional objects, are indifference curves, okay? If these guys are quasi-concave, this three-dimensional object, then this two-dimensional object is convex, right? So that's all you need to know, okay? Now, is that clear? A little bit more clear, okay. So now, basically, let's say a little bit more about the indifference curves and marginal rate of substitution, okay? So this is the link between the utility function, indifference curves. If utility function is this, then the indifference curve should be this, okay? But how will I explain it to my grandma? I can draw these guys. She might get this as well, right? Or I can tell her that, this corresponds to diminishing marginal rate of substitution, okay? So now so let's actually say a bit more about marginal rate of substitution. So more about MRS. Now, remember the definition of MRS was minus dy over dx. And don't forget that the marginal rate of substitution, but it was on an indifference curve, right? So we were keeping utility level at some level k. Okay, so let's say k is element of R, okay? So suppose I have this, u of xy. So this is my indifference curve, right? I know that marginal rate of substitution is what? The slope of this indifference curve, right? That's what we said. So this is actually, it's actually the absolute value of the slope of the indifference curve, okay? So then, what can we actually say about, can we say more about the marginal rate of substitution? So let's try to see. So suppose this is actually equal to k. So remember, I can always take a mono as long as it keeps the order. Remember, in the previous example, we take it to the power 4. Instead, for instance, for this u function, to all of them, I add 5. Do you think this is a positive monotone transform? Do you think this will keep the ordering as well? Right? So suppose my new function, u tilde xy, is this. I take the old utility function and then add 5 to every single number. Do you think this is going to keep the order? Right? If the previous one, suppose, remember our example, u of x1, y1 was giving, let's say, 4, right? U of x2, y2 was giving 5. Now in this new utility function, this guy is giving, instead of 4, this guy is giving basically, right, 9. This guy is giving 10. Did it change the orders? No, right? So this guy is giving me more utility, right? So you see that it doesn't. This is also a positive monotone transformation. Okay, fine. That I know, right? So suppose I have this. So suppose let me define it like this. So let's call it u tilde. I'm going to call this double tilde because somewhere I called u tilde. So suppose u double tilde xy is equal to u xy, right, minus k. Do you think this is going to keep the order? If I subtract the same numbers? It will, right? So now they were giving 4, 5. Now I subtract 5. One is giving, right, minus 1. The other one is giving 0. Still 0 is better than minus 1, right? I would pick so you see that it doesn't matter. So if I subtract a positive number or a negative number, still it's good, right? It keeps the order. Okay, fine. Now you see that this is actually the case. So I call this u double tilde, fine. So and now it's equal to 0. The reason why I made this, you're going to see that because we would like to use a theorem, and the theorem works with 0. Okay, so that's why we took the positive monotone transformation, but you didn't have to. It could also work in the previous way as well. Okay, so now I'm going to remind you a theorem called, do you remember this implicit function theorem? Do you remember that? Remember I told you that whenever we need, I'm going to refer back and forth the mathematical theorems and objects, okay? So let's actually recall this implicit function theorem. So let's write this here. Recall implicit function theorem, okay? So do you remember what that is? Maybe, okay, so we'll see. Suppose we have a function, okay, suppose f of xy equals to 0. That's why I made that transformation, but we know that those transformations are allowed. We don't care, right? So this is suppose f of xy equals to 0. So this defines an implicit, okay, relationship between x and y, right? Sometimes we can solve for this, sometimes we might not. That's the beauty of the implicit function theorem. Sometimes you might not be able to write x write y completely in terms of x, right? So you cannot get y in terms of x. Suppose y is equal to f of x, right? So of course there are some conditions that function, okay, so this f function should be continuously differentiable, etc. Okay, so let's be proper. So all the regularity conditions are satisfied. Okay, suppose this is that, and so let's actually f of y, xy, is not equal to 0. Basically, you know, like the derivative, the partial derivative with respect to y of this f function should not be 0. Okay? Then, suppose you're interested in, so let's put it like this. Then, dy over dx is what? So the theorem says this, but we can just show it very easily. Okay? So we'll find it. So basically, suppose, think of this, so this is the theorem, and we're going to fill this place. So you see, it's not hard. So basically, so write this, f of x, and instead of y, I'm writing f of x. So this is y, basically, right? Equals to 0. Then I totally differentiate with respect to x, okay? So basically, I write this, del f over x, plus, so there's a dx over dx here, so which is 1, okay? And then you also have del f over del y times, okay, because there is a y here, so I take because there's an x inside, right? So, and then I'm going to have del f over del x, right? So let's put it like this. So you can basically, or because it's the function of only x, I can write d. Okay, so basically, so this is equal to 0. So what I did from here to here, I totally differentiate with respect to x. Okay, so that's basically it. So from here, so we know that this is y. So from here, what do I get? Actually, if I'm interested in this derivative, this dy over dx is what? I put this on the side, minus del f over del x, right, divided by del f over del y. You see, what is this? There are many other ways. So this is the partial derivative with respect to x, partial derivative with respect to y, right? So you see the implicit function theorem tells you that even if you cannot write, you know, like y equals to f of, if you can write this, then you can take the derivative immediately, right? But suppose it's very complicated, then it says that you can take the partial derivatives of that function, and then dy over dx would be equal to this. Okay, so this is basically, we actually proved the point. Then dy over dx is equal to minus f of x, f of y, right? The partial derivative of x with respect to x, partial derivative of y with respect to partial derivative of f with respect to y, okay? Now, this is the theorem. This is kind of the proof, okay? So it's not the formal proof, but, you know, it's a proof. So basically, right, so this is it. So now let's try to see what can we learn about this here. What does it say? It says that you can apply this here. Basically, remember, so here this function is equal to 0. And it says that if you're interested in dy over dx when u is equal to k, or u double tilde is equal to 0, right? So we said that, right? The positive monotone transformation, it doesn't matter. So this is equal to what? So basically, according to this theorem, right, if I want to get this derivative, it says that you should write minus, of course, right? So because we know that MRS is this, or we'll do it later, it doesn't matter. So, right, it says that take the derivative of u with respect to x and take the derivative of u with respect to y, right? So that's basically it. So this is actually minus u double tilde's derivative with respect to x, u double tilde's derivative with respect to y. What is this? If I take u tilde's derivative with respect to x, what is it? Okay, that's a nice song. Yeah. So it's actually, right? So what is it? If you take the derivative of this guy with respect to x, for instance, we know that that guy is equal to this. What is it? It's k is a constant, right? It's just u of x divided by u of y, right? Don't worry about this step where I define this other u tilde. You know that they would represent the same information. Just to be formal, I did this. I didn't have to. All you have to know is that you see that apparently marginal rate of substitution is equal to what? MRS. So here you see that we get this using implicit function theorem, right? That's why we needed that theorem, right? Otherwise we didn't know the link. So, but from here we know that MRS is minus of this slope, right? So MRS is what? From here I figured out that u of x divided by u of y. This is probably what you have seen in your introductory class. Marginal rate of substitution, so this is important, is equal to, this is called what? This has a special name. This is basically del u over del x, right? The partial derivative of the utility function with respect to x. We call this marginal utility of x, MUX, okay? And this is similarly del u over del y. This is marginal utility of y. What does marginal utility mean? It means that if I consume marginal utility of x, it means this. So let's say marginal utility, okay, of x. For instance, MUX, we know that this is del u over del x. And basically it means that when I keep the level of, right, y the same, if I consume, let's say, or if you want, you can actually consider this within this context, you're keeping the utility level the same. If I consume one more x, what is the contribution of that x to total utility, right? If I consume one more x, how much extra utility I will get? Basically, this is what we mean by marginal utility of x, right? And it corresponds to the partial derivative of utility function with respect to x, okay? So this is basically the case. So you see with the use, with the help of implicit function theorem, we can show that marginal rate of substitution is equal to this. So this is pretty important. We will use this a lot, okay? So later you'll see. So now we don't need this theorem. I can erase this, okay? Now let's actually have a look at, now remember we said that if I take a positive monotone transformation of a utility function, we said that things won't change, right? They will represent the same information. Now they can represent the same preference relation. That's what we said. Now, fine, but now actually let's try to figure out, so we actually recall our example. What did we say? We had this utility function, x to the power 1 over 4, y to the power 1 over 4, right? But remember, in order to draw the indifference curve, so remember, so we set it equal to 5, but instead of this, we used which one? This one, right? U of xy, which was basically when you put the utility function to the power 4, right? So that's what we said, right? So we actually had x, y. So remember we said, and whenever I was drawing the indifference curve, right, I draw this guy's indifference curve, right? And I said that this represents the same information, okay? Now, if that is the case, you see that and I looked at MRS and such, I said that MRS is decreasing and such. So how do I know that the marginal rate of substitution in this case and in this case, they are the same. They're going to be the same, okay? In this, right? So because if it represents the same information, remember I draw this guy's indifference curve, and I use that MRS, right, in order to understand this guy. So how do I know that MRSs are the same in both cases? Now I'm going to use that property, and you'll see that they are the same, okay? So let's do this. So question, how can we show that they represent same information? Of course, we're not showing it fully formally, but just to have some idea, okay? So how do I know that in both cases, like MRS is going to be similar? So let's have this. So we know that MRS, the marginal rate of substitution, remember by definition, it's actually the absolute value of the slope of the indifference curve, right? But we know that along the indifference curve, you fix the utility level the same, right? So let's put it MRS when utility level is equal to 5 or U tilde is 625, right? So basically, marginal rate of substitution, we actually put U tilde X, U tilde Y. Basically, in order to calculate marginal rate of substitution, I use this guy. How do I know that it's actually marginal rate of substitution of this guy as well? Okay? So basically, this is what we used. Now, let me actually use this. So remember, this U tilde was this, right? Now, I can actually call this one as h of u. So this h function, so this is actually what we did, h of u xy, let's put this. And then remember we had u of xy to the power 4. So this h function here, right, this h function is u to the power 4. This is the function with which we make the transformation, right? So this is actually, and in order to show that it's a positive monotone transformation, this is what we do. You should check this guy. You should check this h guy's derivative with respect to u, okay? And if this is positive, then we call this a positive monotone transformation, okay, of u, for instance, right? It's a positive monotone transformation of u. So in this case, is it? Let's check. U, so h of u is equal to u to the power 4. So let's check. What about del h over del u? What is it? Or d? So this is h, right? So what is this? 4 times u cubed, right? So as long as u of xy, and most of the time that's what we assume, okay, is positive, right? Then this is going to be positive. Then what about this h? So this guy, is it a positive monotone transformation? Yes, right? So let's actually check whether it's a positive monotone transformation. Check this condition. And if it's true, then it's positive monotone transformation, okay? Now, remember our other example, suppose h of u is equal to, another example, minus u. Is this a positive monotone transformation? No, right? So that is actually del h over del u. What is it? It is minus 1, right? And that is negative, so it's not a positive monotone, therefore it's not going to keep the order, right? Then what about, instead of minus u, let's actually think of, suppose, u to the power 1 over 2. Is this positive monotone transformation? If I take the square root of all these numbers. So let's check. What is this? 1 over 2 times u minus 1 over 2. If u is a positive number, right? Then this is positive, this is positive. It is, right? So you see that's also allowed, but the negative one is not allowed, okay? Fine. Now, so after we understand what a positive monotone transformation is, but still my question stands. What is this? So if I want to take the partial derivative of this guy with respect to that, so let me write that down. So let's write it. Now, so let's actually write, if you guys won't mind telling me the, we said that u is equal to 5 or u tilde 625. So this is equal to u of x tilde u tilde, right? U tilde x and u tilde y, right? So what is this? You guys tell me. If I want to take the derivative of this guy, partial derivative of this guy with respect to x, how can I write this? Considering that it's like this, it's a function of u. Right? So it's going to be, right? How would you write del h, right? Over del u times del u over del x. Is this correct? Right? So, and let me actually do it here. Del h over del u over del y. Is it okay? Do we agree? Yes. You see what happens? These guys cancel out, right? And I'm left with this guy, which is u of x, and I'm left with u of y. You see, apparently, we were not doing something wrong. Apparently, the marginal rate of substitution in this case, or if I take a positive monotone transformation of that guy, in this case, they are the same, right? So you see, it's good news that I don't have to deal with these weird functions. I can always convert them to nicer functions like this, and I can compute MRS and everything from there, okay? So apparently, this is actually showing us that. You see that they represent the same information, right? So this is basically the case. So we can actually say MRS, right? U tilde x, u tilde y, ux, uy. So it's the same. Okay, one question. Suppose it was a negative transformation, right? It wasn't. Suppose it was the minus one. And do you think things will change here? Did I use the fact that it's positive at all? This derivative is positive at all when I do this. You see that these guys cancel out. So apparently it doesn't matter for MRS, but we know that it should matter because you know that it's not going to represent the same order, right? It's going to represent completely different ordering. So whenever you work later on, if you come to this point and said that, wait a second, but it doesn't have to be positive, right? These guys cancel out anyways, right? The positive monotone transformation is there so that it would keep the same order, right? If someone says, I like this bundle more than this bundle, then this new transformation also says, this gives more utility than this guy, okay? So if it changes the order, then it's not representing the same preferences, right? So basically, that's why we require it to positive, not for this step, okay? So just keep this in your mind. Now, good news. If you have weird functional forms, you can take positive monotone transformations of them and then use those functions, okay? So use those functions, you can look at those indifference curves and such, okay? Now let's see. Let me actually show you some examples. So let's talk about a little bit more about examples, okay? So this is basically, did you get this? Okay, good. Now, let's actually solve more examples about these guys. But before, I'm going to give you a little bit of, because this is the condition that is given in your book. So if you ever look at your book, and if you want to link to what we are doing, okay, and if you want to understand if you want to understand that condition, let me actually tell you a little bit more about this. So let me write this, more on convexity of indifference curves. So if we, you know that if we want to look at the convex, remember, if the indifference curves are convex, it's related to utility function should be quasi-concave, at least quasi-concave, right? So that's what we said. So basically, so in order to check, for instance, if you're giving a utility function, for instance, and you want to know whether this utility function is quasi-concave, or if you want to know that whether indifference curves are convex, then if you have the utility function, you can check the quasi-concavity of the utility function, okay? So there's another, remember the definition of quasi-concavity that I gave you. There's also another definition in your book, okay, which is like this. Actually, it's a little bit not fully correct, the one. It's a little bit, some portion is actually missing. So we basically, in your book, it says that for utility function to be quasi-concave, for u of xy to be quasi-concave, okay, it actually gives you this condition. U of xx, u of x squared minus 2u of xy, u of x, u of y, plus u of basically y, u of y squared should be negative, okay? Don't worry, I will never ever ask you, that's why I gave the other definitions and kind of the visual interpretation. I will never ever ask this, you know, for you, so you should, you don't have to memorize it. But let's try to understand what's going on, okay? So they say that it's actually a sufficient condition, okay? So if this condition is satisfied, then you can say that u of xy, right, this utility function is actually quasi-concave. Now, but actually there should be another condition, so this is not enough. There is actually an implicit, another condition that should be there. So this is the second condition, okay? This is the one that is given in your book. But there should be another condition, okay, which is actually minus, so it should be f of u of x squared should be negative, okay? So this is additional, it should be there. But your book skipped it, but it's actually for a reason. Now it's a good time. So do you remember that in your introductory econ classes, do you remember a concept called, you didn't see diminishing marginal rate of substitution, but you saw something else, diminishing something. Do you remember? So my 101 students, diminishing rate of returns, that's going to be when we are dealing with the, it's similar with the firm theory. But what else? So my 101 students, for instance, would remember this. This is what I do. I get a bunch of chocolates, okay? So we actually, I just, you know, like invite some students on the stage, and then I made them keep eating chocolate. As they keep on eating chocolate, what do you think is happening to this guy?
It tends to zero.
So it tends, right? It's, what's it called? It's called diminishing marginal utility, okay? So basically, it doesn't have to be there, but most of the time, as you keep eating chocolate, right, it's going to be the extra utility that you get from additional bar of chocolate is going to decrease eventually, right? It might not decrease, and so there are some girls that kept saying higher and higher numbers as they kept eating, okay? But that is actually, you know, like, but eventually, hopefully for them as well, it's going to decrease, right? The additional bar of chocolate at some point is going to give you lesser utility, right? So at some point, it might be even, you know, giving you this utility, right? It might even be, you know, like negative. It is possible. But remember, what did we say? But what did we say?
More is better.
We said that, okay, but what does more is better mean? It means that this is going to give you, more is better means that when you consume another bar of chocolate, this is going to give you additional positive utility, right? It doesn't have to be all the time more, right? But so basically more is better corresponds to what? So this u of x being what? What do you think? Positive, right? So this is basically when you have this actually corresponds to more is better. Because what does it say? It says that when you have one more x, it's going to, the contribution of that x to your utility is positive, right? So it's going to add to your utility. But what does diminishing, bless you, what does diminishing marginal utility means? This guy is actually, if it's diminishing, right, how can I show this? U of xx is negative, right? So this is basically, so this is more is better, this is, right, diminishing, but marginal utility. It's not marginal rate of substitution, okay? Diminishing marginal utility of x. Meaning that, okay, if I eat another bar of chocolate, I'm not puke, you know what puke means, right? Okay, I'm not throwing up, right? So it adds to my utility to some extent, but what it adds to my utility eventually is getting smaller and smaller and smaller, okay? But still, more is better, so it's going to add positively, right? But what it will add is going to get smaller and smaller and smaller, okay? So this is basically, you see that all these math, even these derivatives, they have a meaning, right? So these derivatives, so now let's try to check these conditions. Apparently, for the quasi-concavity, I need this. What does this say? It says that u of x squared, right, should be less than 0, but this is a square, right? So this is positive anyways, right? And there is a minus here, so this is true by, right? So that's why your book doesn't give this, because it's true, right, anyways. And so now let's try to give this, let's try to look at this definition. So what does this say? Suppose we have this diminishing utility of x, let's say. Suppose I have the diminishing utility of x, so we basically have, right, so this is actually, so what does this mean? What did we say? This guy is what? It's a square, it's positive anyways. If there is diminishing utility, what is this? Negative. Fine. If there is more is better, we know that this guy is positive. If there is more is better, this guy is also positive. Also true for the other good as well, right? What about this guy? Negative, right? And we said this guy, it's a square, it's positive anyways, right? Unless it's 0, obviously, right? So this is actually the case. Fine. Now you see that this part is negative, right? So let's try to see. This part is positive. Can I say something here? Okay, so let me ask. I know this part is negative. So good, negative, negative. Here this part is positive. I have a negative here, but can I say overall this is always going to be negative? What do I need to know? This cross partial I need to know, right? What is this guy? You see that actually from here you are making this link. Even if I have diminishing marginal utility, right? I have diminishing marginal utility and I have more is better. But you see that diminishing marginal utility is not the same as, remember being quasi-concave was equivalent to what? Diminishing marginal rate of substitution. Apparently, diminishing marginal rate of substitution and diminishing marginal utility, are they the same thing? No, right? Because it doesn't, if there is diminishing marginal utility, it's not necessarily the case that you have diminishing marginal rate of substitution, right? Remember, checking quasi-concavity, it also means that whether there is diminishing marginal rate of substitution. If quasi-concavity condition is not satisfied, It doesn't necessarily mean that, right? If I have diminishing marginal utility, it doesn't necessarily mean that I'm going to have diminishing MRS, right? Because you can also think of this as a condition for diminishing MRS, okay? So you see that the condition in your book, it is there to check for the quasi-concavity, but you'll see that we're never going to use it. But to understand what it means and how it's linked to the concepts, it's actually like this. Apparently, it means that there is diminishing marginal rate of substitution if this condition is satisfied. But we know that if you have diminishing marginal utility of x, diminishing marginal utility of y, it's not enough to guarantee that MRS is diminishing. Okay? Is that clear? Okay. So this is basically those, so these are actually the conditions. So let me show you one example, and then we'll stop. Okay? So let's check. Now, example. So these are two different concepts, okay? Students usually tend to, get confused about them. If you have one, it doesn't necessarily mean that you have the other, okay? So diminishing marginal utilities does not guarantee diminishing MRS, okay? Now, some examples, right? So suppose if I ask you whether these indifference curves, so suppose this is the first one, u of xy is this guy, y to the power 1 over 4, okay? So suppose I want you to check whether indifference curves are strictly convex here. What can you check? So you have different ways, right? One, you can use this utility function, use this ugly condition, and check whether the utility function is quasi-concave, right? Do you want to do that? No. Okay, so another thing, what you can do is that you can actually try to write another way of doing it. You can try to get the indifference curve, and then get the indifference curve's equation, and then use the convexity definition that I gave you, and then check whether indifference curve is strictly convex. Do you want to do that? Maybe, right? But there's an easier way. What can we check? We can look at MRS, and we can check MRS, whether MRS is decreasing, right? Remember, those were all equivalent, right? So let's check whether we have actually, MRS is actually decreasing here, okay? Now, if I want to compute MRS, shall I compute it from here, or I should be smarter? So remember, what was MRS? I need to have this, u of x, u of y, right? So think of a transformation which is going to make my life much easier, because I know that if I take a positive monotone transformation of this guy with some function h, I'm fine. Think of it when I can get easy, because you can take derivatives of these guys with respect to x and y. Of course, you will later on. But there's an easier way. Think of a transformation. How do we get rid of these exponential stuff? What do we use usually? There is a function. We take fourth power, but then it will still be, of exponential form. What do? We take logarithm, right? So let's do this. So now my h is let me think of my u tilde xy ln u of xy. Then what's going to look like if I take the logarithm of this function? It's 1 over 4. Right? Plus 1 over 4 ln x plus 1 over 4 ln y. Now, if I take derivative of these guys, isn't it easier? So tell me the derivative with respect to x. 1 over 4, 1 over x. 1 over 4, 1 over y, right? So these guys cancel out, y over x. If you want, you can try, if you didn't take the transformation, because remember we proved it anyways. If you here, even if you didn't take the transformation and took the derivatives of the original function, you would get the same thing, right? But you see, this is much easier. But how do I know that logarithm is a positive monotone transformation? Remember what I was checking? I said that, oh, this is ln u, h of u is ln u. I take the derivative of this guy. What is this? The derivative of this guy with respect to u? 1 over u. And as long as utility is positive, and that's what we assume, because we assume x and y are actually positive in the asymptotes as well. So this is going to be positive, okay? As long as this is positive, this guy is positive, right? So basically, it's a positive monotone transformation, which is allowed. I can use it. Then I can use its derivative, which is much easier. And then this is going to be y over x, okay? So what can you say about this? Is MRS decreasing? We'll say this and then we'll stop. It's okay, but just be careful. Don't forget that as x increases, what's happening here? As x increases, what's happening here? As x increases, x is increasing. We know that MRS is decreasing. But is it the only way that this is when x changing, and when x is changing, things are changing only because of this guy? Remember, if I change x and if I'm on the same indifference curve, what's happening? So it is also right. Remember, so if I'm changing x, then also I know that to keep utility the same, y should be decreasing, right? So it's not only as x increases, okay, this guy, so let me write this, MRS decreases, okay, but due to two reasons. Because x is increasing, right here, the denominator is increasing, and the other reason is that y would be decreasing, okay? Don't forget that MRS is a concept where we keep utility the same, right? It's the slope of the indifference curve. So y is decreasing. So you see that this guy is increasing, this guy is decreasing. Overall, what's happening to this guy? It is decreasing, right? So we can actually show that as x increases, MRS decreases. So we have actually strictly convex indifference curves here, okay? You see that I don't have to check this ugly condition. I don't have to check that convexity condition, ugly. I can check this guy, okay? So we'll continue on Friday.